Hi all, in this video we're going to look at continuous random variables and the normal distribution. Question 1. Let x be a continuous random variable with a probability function given by fx equals ax squared, where a is a constant. Calculate the value of a. If x is a continuous random variable, then the probability, being a probability density function, the area under the curve between 0 and 3 must equal 1. Hence, we now integrate by using the power rule. We'll add a power, so that becomes a 3, and we'll also divide by 3. We're now going to evaluate using the terminals 0 and 3. If I sub in a 3 and I sub in a 0, 3 to the power of 3 is 27, divided by 3 is 9, so 9a equals 1, hence a equals 1 over 9 by dividing both sides by 9. Now we know a, the function fx, is 1/9 x squared. So to determine the probability that it lies between 1 and 2, we're going to integrate fx between 1 and 2. So again, using the power rule, we add to become a 3. We also divide by 3, so that 9 becomes a 27. Evaluating the definite integral, we're subbing in a 1, we're subbing in a 2, and our calculator can then do the rest for us, unless it's a tech-free exam. The probability is 7 over 27. Question 2. X is a continuous random variable with a probability density function defined by fx is half x between 0 and 2 and 0 elsewhere. Calculate the mean of x. The expected value of x is x times fx, and we're integrating that function between 0 and 2 because that was the domain for that function. So we multiply fx by x, we have half x squared. So we're going to integrate a half x squared between 0 and 2. Using the power rule, we add a power, so we now have a 3, and we divide by 3, so 2 times 3 is 6. Evaluating the lower and upper terminals, if we sub a 2 in, 2 to the 3 is 8, 8 over 6 is 4 on 3. That's the mean of that probability density function. Question 3. Sketch the graph of the following function, fx equals 0.5 between 4 and 6 and 0 elsewhere. Now 0.5, think of it as y equals 0.5, which is a horizontal line which is always 0.5 high. Now it only exists between 4 and 6, and that's our sketch. Now here you've got 0 for elsewhere. Is this function a probability density function? Explain your answer. The area bounded by the curve and the x-axis, which is here, needs to equal 1. Simply put, you could integrate it and then evaluate it between 4 and 6, but you've got a rectangle that's 2 wide and 0.5 high, so 2 times a half is 1. Question 4. A study on 70 people was conducted to record the time taken to complete a 50-meter hopping race, where x is the time taken in seconds. Determine the probability that the time the person completed the race in was between 40 and 50 seconds. So between 40 and 50 seconds. We can just use the values in this table by using the total frequency being 70, the probability being the number of successes divided by the number of events. Here we have between 40 and 45 being 14, and 45 and 15 being 11. 14 plus 11 divided by 70 is 5 over 14. B, less than or equal to 35 seconds. So that's the values from here all the way up to here. So the probability that x is less than 35, the sum of 11, 7, 4, and 2, divided by 70, which is 12 on 35. Question 5. Validate using integration techniques that fx equals 4e to the negative 4x is a probability density function. We've got to integrate this and actually show that the area under the curve between 0 and positive infinity is 1. Now, if we integrate e to the power of something x, the k value, negative 4, we divide by that because the derivative of negative 4x is negative 4. So we divide by that and keep e to the negative 4x the same. 4 divided by negative 4 is negative 1. Now we're going to evaluate the definite integral. Note that I've rewritten this using positive indices. So it's negative 1 over e to the 4x. I've subbed in infinity, I've subbed in 0. 1 divided by e to the 0, well, e to the 0 is going to be 1, so it's 1 over 1. but you're going to have to take a negative number, which is why it's a positive. Regardless of this being a negative or positive, 1 divided by an exceedingly large number is going to approach 0. Hence, it's like a limit question. 0 plus 1 is 1. As the area under the curve is equal to 1, it is a probability density function. The next question is to work out the median wait time. So a definite integral between 0 and some value m has to equal 0.5. Since we've already evaluated the integral here before, anti-differentiated, we can sub in m and sub in 0. Similarly, this one's going to turn into a 1. This is negative 1 over e to the 4m. So to rearrange this, we're going to subtract 0.5 from both sides, and then we're going to add this to both sides. The left-hand side is a half. So now we have 1 over 2 equals 1 over e to the 4m. You could just flip this, so that way it becomes 2 over 1 equals e to the 4m over 1, or really equate the denominators. 2 equals e to the 4m. You now take the natural log of both sides. Log base e2 equals 4 to the m. Divide both sides by 4, and that's your exact value. Question 6. The continuous random variable x has a probability density function given by fx equals ax between 0 and 4 and 0 elsewhere. Apply algebraic method to determine the real value of a. We know that if this is a PDF, the area under the curve between 0 and 4 must be 1. So if we integrate between 0 and 4, we can determine a. Using the power rule, x becomes x squared, we have to divide by 2. Now if we sub in 4, 4 squared is 16, 16 divided by 2 is 8, so therefore a is 1/8. So fx equals 1/8 of x. Now calculate the mean to 2 decimal places, that's x times fx between 0 and 4, and that's a definite integral. Multiplying 1/8 x by x, you get 1/8 x squared. If we integrate that, it's going to become x cubed, 1/8 divided by 3, which is going to be 1 over 24. If we integrate or evaluate those terminals, if you sub in 0, it's going to be 0. If you sub in 4, what you're going to be doing then is 4 cubed divided by 24, which is 2.67, which lies between 0 and 4, and that's the mean value. Question 7, we've got a continuous random variable with a PDF function given by 1 over p times 9x take x cubed, where p is an integer constant. Calculate the 2 to 3 decimal places the values of p, the mean, and the median. Like the previous example, the area under the curve between 1 and 2 has to equal 1. So we're going to write up an equation, which is the definite integral on the left, and it's all got to equal 1. We're going to take out this constant 1 over p, this coefficient, and now integrate the 9x take x cubed. Applying the power rule, x becomes x squared, we've got to divide by 2. X cubed becomes x to the 4, we divide by 4. This 1 over p, the opposite of dividing by p is the times by p. Left hand side, we evaluate by subbing in the terminals. The lower one is 0, which is going to be 0. If we sub in 2, like I have here, and get a calculator, we're going to have 18 take 4, which is 14, and our p-value is now found. Now to work out the mean or expected value is x times the function. So x times 1 on 14 is what we want to do. Taking out this 1 on 14 and timesing x through, so x times 9x is 9x squared, x times x cubed is x to the 4. Integrate. So using the power rule, we get 3x cubed, take 1/5 x to the 5. I'm now going to sub in 0, and I'm going to sub in 2, and our upper boundary, take our lower boundary, is 1.257. Part 2, the normal distribution. A random variable x is normally distributed with the mean of 15 and a standard deviation of 1.5. If x is 19.5, calculate the standard normal random variable z. So z is x minus mu over sigma. Our x is 19.5. Take our mean divided by our standard deviation. The z score is 3. 3 actually is 3 standard deviations above the mean. Determine the probability of x being less than 19.5. So using our stats menu, then choose distribution, the normal cumulative. You don't use MPD really ever, it's NCD. Now, our data is a variable. Now, because I'm doing less than 19.5, which was actually a z-score of 3, I'm using the z-score here. So my upper boundary is 3, my lower is, technically your smallest z value is going to be about -3 or 4. I just write a -999 just to make it easier. My standard deviation of a standard normal curve is 1, and my mean is 0. Press enter, and the probability is 99.86%, 865%. So the probability that x is less than 19.5 was the probability that z is less than 3, which is 99.87%. Probability that x is greater than 19.5, that's thinking of it as z being greater than 3. If I know the answer here, to the left, the right-hand side is going to be 1 take that. So 1 take 99.87% is 0.0013. You could also do it in the calculator by choosing it to be a lower boundary of 3 and upper boundary of, say, 999. So here, lower is 3 because I want to be bigger than 3. My upper is 999, and I get that answer, which is over here. Calculate the value of A, given that for a standard normal distribution Z, the probability of Z being greater than this value is 0.9. So we're a Z-score where above us is 0.9. So to the right on a normal curve is 90%. You look at it in two ways. You could solve it on a calculator, or you could think, well, actually, Z is also less than A, which is going to give us 0.1, which is the remaining area under the curve. Now, if you use the inverse normal calculations on your calculator, A is actually a negative Z-score, which is negative 1.28. Or better yet, we use a stat mode. The calculator will go to our stat mode and choose distribution, which is here. We'll choose inverse normal, meaning you want to find the answer instead of, you know the probability, the area, but you need to know the A value. We're just saying greater than, that's to the right, and our area is 0.9, our standard deviation is 1, and our mean is 0. And press enter, and the answer is negative 1.282, which we have up here. For a standard normal distribution, calculate the following. The probability that Z is greater than negative 0.25. If you had to use the old school days of Z-score tables with only positive values, you'd have the probability of Z being greater than negative 0.25. It's the same as using symmetry, Z being less than 0.25. If I did that on a calculator or tables, you get 59.87%. Being that you've got various calculators to do the work for you, you can go to the normal CD function on your calculator. You are saying the lower boundary is 0.25, negative 0.25, which you're saying greater than. Your upper value is 999. Again, 1 and 0. The answer is 59.87%. Next is working at the probability that something lies between negative 0.5 and 1 Z-scores. Here, our lower limit is negative 0.5, our upper is 1. 1 and 0 are a standard deviation and mean again. And simply put, using a calculator, the area between those 2 points is 53.28% of the curve. If you have to use Z-score tables, you'd have to, same again, you've got your probability between Z being between -0.5 and 1, which is your furthest right one, take your furthest left. So the probability of Z being less than 1, take the probability of Z being less than -0.5. If you didn't have negative Z-score tables, you'd have to then use symmetry here, work out your values, and you get the same answer. But you've got a graphics calculator, so it's all been simplified for you. Technology active. If X is normally distributed with the mean of 10 and a variance of 2.5, calculate the probability that X is less than 12. So your mean's 10, your variance is 2.5, take the square root of that, and that's your standard deviation. The probability that X is less than 12 is the probability that your Z-score is X minus mu over sigma. So your Z-score is less than 1.265. That answer, using tables, is 0.898. Applying a calculator as the alternative, just remember to change the mean and standard deviation. So here we're going to go NCD. Since we're saying less than 12, our upper is 12, our lower, I still choose -999. My standard deviation is this 1.58, which is the square root of 2.5. The mean is 10. Press enter, and you get 0.89, or this time we get 897. So that must be a little typo there. So our area is 0.897. This would have been rounded, which is why the Z-scores would have been slightly off. Next one, we're going to work out the probability that X lies between 10 and 14. This is the Z-score approach, which you'd have X minus mu over sigma, X minus mu over sigma. So you're actually working out the probability that your Z-scores lie between 0 and 2.5298. In that case, you'd be looking up Z-score tables and getting an answer of approximately 49%. The calculator is just as easy, or probably easier, and that your lower boundary is 10, your upper is 14, there's your standard deviation, and your mean, you get 49.4%. Question 13. The probability that Z is less than -0.376, where Z is a standard normal random variable, is which of the following? We can just apply technology here and use our NCD button. Our lower boundary, I'm just going to keep writing -999. Our upper boundary is this, -0.376. Our mean is 0, standard deviation 1. We press enter, and the answer is 0.35. Closest to that is B. The next one, if Z is a standard normal random variable, where Z is greater than a value equals 0.75, then C is closest to which of these? You could use logic here. If you're greater than, you are to the right. If there's 75% to the right of you, you have to be a negative Z-score. Because halfway is 50, so you have to be the left-hand side of that halfway mark, the mean. But we don't have to. We'll use the inverse normal, where to the right is 75%, 1 and 0 again, and that Z-score is -0.6744. Here, our value is A. The random variable X is normally distributed with a mean of 10 and a standard deviation of 1.5, and the probability that X lies between 8 and 11 is closest to what? We can choose our NCD button again. Our lower is 8, our upper is 11. Remember to change your standard deviation and mean, so they're not 1 and 0. And the answer is 65.63%, which is D. The volume of liquid in a 1.5 litre bottle of detergent is normally distributed with a mean of 1.6 litres and a standard deviation of 0.06. The percentage of bottles that contain more than 1.5 litres of detergent is closest to. We're going to use our normal distribution button, which is our cumulative. Our lower is 1.5 and our upper is 999. my standard deviation is 0.06, my mean is 1.6, and that's 95% of all bottles, which is E. Which one of the following random variables will be normally distributed? The number of sixes observed when a die is tossed 3 times, that's discrete. The length of time it takes to travel to school each day in minutes, the length of time can take on any value. The number of times a coin is tossed, that's a discrete value. The number of female children in a family of 5, that's a discrete. The number of red balls is again counting, so that's discrete. Answer is B. If X is normally distributed random variable with a mean of 60 and a standard deviation of 10, and Z is the standard normal random variable, then the interval shaded in the diagram below can be written as. We've got to try and think of this as Z scores. If this is our mean, and I am 10 above that, if I went X minus mu over sigma, 70 take 60 would be 10, divided by the standard deviation of 10 would be 1. Here you can see some of these Z scores are 1. So I'm going to do that for you. I'm going to work out the Z score for 70. 70 takes 60 over 10 is simply 1. The other Z score would be 40 takes 60 over 10, which is negative 2. So if I transform this into a standard normal random variable, the Z scores would be 1 and negative 2, which is D. Scores on an exam are known to be normally distributed with a standard deviation of 10. If 3% of the people who sat the exam scored more than 90 marks, then the mean examination score is closest to which value? Here we're going to use our inverse. So determine the Z score that represents a right tail area of 3%. I'm going to choose a right tail because above me is 3%, and I want to know what Z score that is. Now the Z score for that is 1.881. Now, since I know the Z score, I can use the Z score rule because I have the standard deviation. I know the mark, I've just got to work out the mean. So apply the Z score rule to determine the population mean. Recall your rule. Now, Z score was 1.881. The kids were getting 90 marks. I don't know the mean. The standard deviation was 10. Let's multiply both sides by 10. Now we'll rearrange. Mu comes over this side. We'll take 18.81 from both sides. That mean score was 71.19. Question 18. For the standard normal random variable Z, the probability that Z is less than negative A equals P, and A is greater than mu. Calculate the following in terms of P. First one, what's the probability that Z is less than A? Less than or equal to A. So you think about this. The first one was the probability that Z is less than that negative A. So there's my negative A. I mean, it's got to be on the left-hand side of the mean. So negative A I'm making here, and the area behind me is P. So the leftover area is 1 take P, because all this area's got to equal 1. So the probability that Z is less than A would be, using symmetry, A would be over here. In front of it would be P, like this one, and behind it then must be 1 take P. So the probability that Z is less than or equal to A is 1 take P. The area, or expressing a probability statement for negative A to A, there's my A, there's my negative A. To the left of it was P, to the right of it was P. So that area in here is all of this is 1, take a P, which is 1 take 2P. 19. Let X be a normally distributed random variable with a mean of mu equals 7 and a standard deviation of 2. Z is the standard normal random variable. Calculate the following. If probability of X is less than 3, it equals the probability of Z being less than what? This is actually quite a simple question. All they're asking you to do is work out the Z score. So for A, we'd have our Z score, X being 3, minus the mean, divided by the standard deviation. The Z score is negative 2. So A is negative 2. For B, 8 take 7 divided by 2 is a half. So B is a half. Question 20, we've got x being a normally distributed random variable with a mean of 5 and a standard deviation of 2. If the probability of z being less than 1.64 is 95%, where z is a standard normal random variable, calculate c such that the probability of x being greater than c is 95%. What you got to see here is this can be thought of as a symmetry style question. The areas are the same. One's a left tail, one's a right tail. So they're actually telling you the z score up here that gives you 95%. So if I'm a left tail, I'm positive 1.64. So if there's 95% in front of the same z score or similar z score, it'd be negative 1.64. So now my z score rule, z equals x minus mu over sigma. My x I don't know, my mu is 5 and my standard deviation is 2. Rearranging, multiply both sides by 2, then add 5. That score would be 1.72. That c value, x would be greater than 1.72 to ensure that to the right is 95%. A continuous random variable, x, is normally distributed with the mean of 45 and a standard deviation of 6. If the probability that x is less than k is 45, calculate the value of k, correct at 3 decimal places. That's going to be using a stat menu, using the inverse, because we know the answer. Less than means left. The error is 45%. The standard deviation is 6 and the mean is 45. You press enter. Therefore, k is 44.246 to 3 decimal places. If x is a normally distributed random variable with a mean of mu and a variance of 0.35, and the probability of a certain score, like x being less than 6, is 85%, calculate the mean of the normally distributed variable x. So let's first of all write a variance being 0.35 and a standard deviation is the square root of 0.35. The probability that you're less than 6 or x is less than 6 would be a z score. So 6 x minus mu over sigma, so 6 minus mu over sigma. Using our inverse normal distribution function on our calculator, we want to work out a z score that makes this true. So we can figure out the z score, we can then use it to solve for mu. So to the left is 85%. I'm using a standard normal values here of 1 and 0. Finding from that, I get 1.036 is my z score. So now I can sub that in. So my z score is 1.036. Now I can just rearrange and solve for mu. So I'm going to multiply both sides by the square root of 0.35. Then I'm going to rearrange, and my mu is 5.387. Question 23. A battery company states that batteries last according to a normal distribution with a mean of 22 hours and a standard deviation of 4 hours. Determine the percentage of batteries that will last longer than 15 hours. This is a simple calculator question. My lower is 15, my upper is some very large number like infinity. My standard deviation is 4, the mean is 22, and our answer is about 96%. The probability that x is greater than 15 is 0.9599. Therefore, approximately 96% of the batteries will last longer than 15 hours. If it was done z-score days, here we work out a z-score. We then try and work out the probability of it using z-score tables by writing it in terms of being greater than a z-score, or using the symmetry, and then we look up our tables and get 95.99% as well. This is your technology focus. Question 24. The weights of packages of chocolate fudge biscuits produced by the Aviation Biscuit Factory are normally distributed with a mean of 750 grams. If a package of biscuits is more than 6 grams underweight, it is not acceptable. It has been found that 3% of the packages are unacceptable. Determine the standard deviation of the weights of chocolate fudge biscuits packets produced by Aviations. Give your answer correct at 2 decimal places. The mean is 750. The probability that whatever package of biscuits here, X is less than 744, is 3% they're telling us, which is 6 grams underweight. So 750 take 6 is 744. We then have to figure out a Z-score. So 744 take 750 over sigma, being less than that Z-score is 3%. So if we use our inverse normal and our left tail is 3% with the standard deviation of 1 and a mean of 0, the Z-score is negative 1.881. So using that statement here, using the inverse normal button, we can now use, we found that the Z-score is negative 1.88, we can sub it in here. So 744 take 750 over sigma equals a Z-score of negative 1.88. We can then rearrange. 744 take 750 is negative 6. We can rearrange and find the answer is 3.19. The standard deviation of the weight of chocolate fudge biscuit packets is 3.19 grams. Question 25. In the English exam, Alex's score is the same number of marks below the class average as Bartholomew's score is above the average. For this exam, the class average score was 42 and the standard deviation was 10. If 52% of the class achieved scores between those of Alex and Bartholomew, determine the scores achieved by Alex and Bartholomew. Let A equal Alex's score and B equal Bartholomew's score. And the probability that the score lies between Alex and Bartholomew's score is 52%, because 52% of the class achieved scores between those two. Now my mean is 42 and the standard deviation was 10. As A and B are equidistant, like equal from the mean, the probability that X is less than A is 50%, take your 0.26, which equals 0.24. Think of it as a diagram. Here's your mean. If 52% lies in the middle here, so this coloured in area is 52%. There's one kid, there's the other kid. This coloured in area is 52. Half of it is 26. So there's 26 here, there's 26 here. Now there's 26 here, this must be 0.24. Now you just need to figure out the Z-score. So a certain Z-score produces an area of 24%. So X minus mu over sigma has to produce 24%. So using the inverse calculator button on our Gravix calculator, we get the Z-score as being negative 0.706. We then multiply both sides by 10, add 42, and A is 35. Now if this kid, Alex, is 35 and the mean's 42, he's 7 marks below the mean, which means that if Bartholomew is the same above, we go 42 plus 7, and he would be 49. Alex's score was 35, and Bartholomew's score was 49. That's the end of general continuous random variables and the normal distribution. Keep studying, and good luck on your exams.